This warm-up is having you make expressions for each type of figure, given a particular side length. Like for example, figure A, and it says is a large square, so what's unique about squares? Okay, good. The main thing is that all their sides are equal, and how do you find area of a square? Good, and that's how you find it for really any rectangle or square, but for specifically squares, you could even change that because since their sides are all equal, you could just make that side square. Okay, because it's gonna be like multiplying the same number, so you can even minimize it further and just do whatever the side length is, square. So that's why when the side length is 4, the area is 4 squared, which I'm sure you could even simplify further and get 16, which is also correct. What about table 1? What about when it's x? What will be the area for A? Okay, class, agree, disagree, thumbs up, thumbs down. Okay, yeah, why not? If the side is x, then the other side must be x, length times width, x times x, or x squared, because you just said squares could be side squared. Good. Table 2. What about if the side length is 4x? What would be my area for A? Would it be written like that? Okay, who thinks yes, that we should leave it like that for that one? Who thinks no? Okay, so how can I make this better? What do you think? Well, you do need the square, Landon,
Parentheses on the x,
around just the x.
or 4x.
Okay, so parentheses around the 4x. Because technically, in this case, it would be 4x times 4x. If you just put the squared on the x, that would imply that it's like 4 times x squared, or something like that. Because you could simplify that further. What's 4 times 4? What's x times x?
And
X squared, and if you just put 4x squared, that's not the same thing. Does that make sense? So really you could write this or this in that box, both would be correct. All right, but it's the side length squared. Let's see, table 3, how would we write that last side length as the area of A? X plus 3 parentheses on the square. Okay, good. Or you could also expand it, do the x plus 3 parentheses times x plus 3. Both are equivalent, but yeah, basically side length squared. Questions on that? All right, now how is figure B different than figure A? Tell me, table 4.
it has a square.
Good, it has a square in the middle of it. Is it shaded? No, so that means it would be like cut out of it. So if I was trying to find the area of this figure, it's whatever the square is minus the area of the part that's cut out. Do we know what the area is of the part that's cut out? What is it? 1, because it has measurements, right? If area of a square is a side length squared, then that little area is 1. So that's why for this row that's filled in, that's why it's x squared minus 1. It's whatever the area is normally, which we said would be x squared if it was a normal square, minus the area of the cutout. Make sense? Okay. So then table 5, what would the area be for B if the side length is 4? Alright, class, does that work? Yeah, and we could even simplify it further. We could do 4 squared, which is 16, minus 1, which is 15. So if you put 15, great. But this works too. Table 6, what would it be for this row? Would you say minus what? Okay, class, is this perfect? How can we fix it? Okay, good. And maybe that's what you had written down, but just, you know, from what you said, it didn't sound like it, but if you had it written down, great. You do need to have the parentheses around the 4x to show that you do, the power of 2 to both parts in there, if that makes sense. Okay. Or you could write 16x squared minus 1 if you want. The other ones, we don't have to do that because we would do exponent first anyway, right? But this one, there's multiple things that need the exponent of 2, so you have to make sure you specify it. All right, table 7, what about that last row for B? Just like that. Okay, good. X plus 3 in parentheses. Otherwise, they would do the squared on the 3 first, but really it should be added to the x first. So yeah. All right. Then table 8. How is figure C different from all the others? It has 2 squares, or like 2 of the same size squares, and then a little square. So if I need to find the area of that figure, do I include the additional boxes? Yes, so we know that these squares are like equivalent to each other, right? The one side of the square is 4. How can we write the area of C? Let's rotate the recorder 1 to the right. Because now we're back to the front. Okay, so table 1, 1 to the right of the recorder last time. What would the area of C be if the side length is 4? Okay, so that accounts for this little box and one of the squares. How can we account for another one of these? That works. It really does. What else could I have done, Table or Brian?
Did 2 and 1 parentheses, the power 4 plus.
Good, you could have done this, which is also the same thing. Okay, so either one works. But yeah, that works. Questions on that? Because either way, you'd still get, well, I mean, 16 is what you get from doing 4 squared. 16 times 2 is 32. And if you do 16 plus 16, you still get 32. So same thing. All right. Table 2. What about when it is x for the side length? All right, class, looks good. All right, I agree. Looks good for that one. Table 3, what about that last row that's not filled? 4x is the side length. What would the area of C be? Okay, good. And notice, the 4x does need to be alone in the parentheses. In these other ones, I attached it, but even if I didn't, even if I did just the input, probably should have just done the input. You would still get the same answer. because you do exponents first. All right, so maybe I should adjust it to that, but either way, that's what it looks like for that row. And then the last one's filled in for you, which also makes sense. 2 times whatever the side length is squared plus 1. So questions on the warm-up? All right, I like these. They prepare you really well for your state testing. They love to put these types of questions where they give you area of weird figures. And then you have to like problem solve your way out of it. All right, so now with your groups, you're gonna do this activity. We have, if the pattern continues, what will we see in step 5 and step 18? Also at the same time, I think number 2 is a good strategy for figuring out the answer to step 1. So how many small squares are in each step? Explain how you know, and then maybe go back and do number 1 to see what it'll be in step 5 and step 18. Okay, so I'll give you 3 minutes and then I'll check in. I think that'll be enough time if you've been, understanding the last 2 lessons. But if not, here's another chance to try that out with your groups. Raise your hand if you think you know the answer for step 5. I'll just take all of the answers, see which one's right. Sure. So Brian? What did you say? 24. Any others? Anthony? 29. Any others? For step 5? Okay. What about step 18? What do we get? Landon? Okay, 328. Anyone get something different? Brian? 323. And any other answers in those? Okay, so I'll read you what the book says. The answer that it agrees with is that step 5 has the 25 small squares surrounded by the 4 little squares. So that total would then be 29. And then step 18 would be a collection of like 18 by 18 squares. So that would be 320. Let me just make sure. I actually don't know what that is off the top of my head, but then they add 4 to that, which gives you a final answer of 328. So those 2 answers, let's see why, because again, this will show up on your test. So here's how you can figure it out. Step 2 or question 2 says how many small squares are in each of the steps. So like how many squares are in step 1? How many in step 2? And step 3? Okay, so when you're doing these, we've only learned like 3 different types of patterns. Just kind of process of eliminate. Is it linear? And how do you know? So linear, it's not about multiplication, it's about adding. So is it adding by a consistent amount each time? No. So it's not linear. See if it's exponential. How do you know if it's exponential? If it multiplies by the same amount each time, is it doing that? No. So then see if it's quadratic, because that would be the final one. For the quadratics, what we've noticed is that there seems to be a pattern within the differences, if that makes sense. So going from 5 to 8, we get +3. From 8 to 13 is +5. So then to go, say, to like step 4, what would I add? What was that?
7.
7. So it's like you're finding the pattern within the numbers that are the differences, if that makes sense. So then in step 4, I have 20 squares. And then in step 5, what would I add to keep this pattern going?
9.
I would add 9, which then gives me a grand total of 29 for step 5. Thank you. All right, so to figure out step 5 that way is not a bad strategy because it's pretty close to what we currently have. I bet some of you drew and got the right answer, like you drew the next few steps. But is that really easy to do when we have to go all the way to step 18? Probably not. So that's why knowing what type of function it is, so we just figured out it is quadratic. Knowing what type of function it is, we could make an equation to figure out that step 18. So since it's a quadratic, what does it need to have? At a minimum? An x squared or an n squared, something like that. That's the minimum requirement for it to be a quadratic function. So for me to help make the equation, I look at my step numbers. So like for step 1, 2, 3, there were 5, 8, and 13 squares. Since it has to have a quadratic, and that's what would be x squared, I square these. So like what's 1 squared?
1.
And then what can I do to 1 to get 5? Okay, so we can add 4, see if it stays consistent with the rest of these, because other people have said, oh, well, you can multiply by 5. Yes, that's true, but does it work for all of them? So like what's 2 squared? What can I do to 4 to get 8? I could add 4. Try it with 3 squared. What's 3 squared? What can I do to 9 to get 13? And that's like its own pattern in itself. So to make the equation, we could write what? What are we doing to? Good. All right, so my question was going to be, what are we doing to the step number? What are we doing to the x each time? We're squaring it and then adding 4. So that's going to answer number 3. And they wanted you to use n for step number, so I just switched it for the n. And then when we try to find step 18, where do we plug in that 18? For the n, so then it becomes 18 squared plus 4, which is how we get the 328 for question for step 18. All right, questions on that? So that's much more like time effective than just continuing the pattern 18 times. All right. Now number 4 says sketch the first 3 steps of a pattern that could be represented by this equation. All right, n squared minus 1. So now it's like you're working backwards. Now they're giving you the equation. You draw the steps for the first 3. Right, don't overthink it. It's actually much easier than you might think. But I'll let you finish first. So for step 1, 0 is correct. How do we figure that out? Okay, 1 squared minus 1. So the step numbers are kind of like your inputs. So in this equation, the input would be where the n is, not the y, because that would be an output. And 1 squared minus 1 is 0, right? You have nothing sketched for step 1. What about for step 2? Right, Brian? Okay, we have 3 squared. Anyone get something other than that? All right, I put dots, that's fine. No? All right, so for that one, you plug in the step number for n. N represents step number. N represents like nth term. So whatever term they want you to find, like the second term, you just replace for the end. So 2 squared minus 1, what's 2 squared?
4,
Minus 1, you would get 3 squares dot product. Step 3 then would have how many class? If you said 8, then you're correct, because 3 squared is, and then minus 1 is. All right, the book specifies that it should be like in the shape of a square with 1 missing. I don't know that that truly matters, but I think what they're trying to get you used to is that quadratics are x squared, right? So like this whole like square part of it is like really important to them. So if you see that it's growing by like a similar pattern to what we've seen, then you could assume it's quadratic, but here's how you really know, is by attaching it to numbers and seeing the pattern within that pattern. So questions on that? All right, so 3 and 4 are combined. Don't worry, it's one homework for the 2 lessons. It's already in Schoology. All right, but now we're on this activity. So which one grows faster? So pattern A, which is pictured below, the length and width of the rectangle grow by 1 small square from each step to the next. In pattern B, the number of small squares doubles from each step to the next. In each pattern, the number of small squares is a function of the step number. So like the step numbers are the inputs. You're going to write an equation to represent the number of small squares at step n in pattern A. Then figure out, is it linear, quadratic, or exponential? And then use the table. So questions on what we're doing? Okay. Let's try that. My first hour didn't get to this part, so let's see how it goes. I'll give you, again, 3 minutes. All right, for pattern A, so let's fill out the table. I think that's a helpful first step. I don't know why they always tell you to do that last. But in step 0, how many squares do they have? Step 1, step 2, step 3. Okay, based on even just this, can you tell me if it's linear, quadratic, or exponential? Okay, good. So if you didn't have that written on your paper, maybe write that down. Pattern A is quadratic. And how do you know? Because they're squaring the step number, so that's a big indication. Quadratics have an x squared in it, so they're squaring this, and they could be doing other stuff to it, but in this one they're just squaring it, so that's really easy then. And then I think Brianna, it was you that brought up a good point. It's not adding each time, it's not multiplying each time, so it's clearly probably quadratic, the other option. Okay, so yeah, then when we continue this pattern, what's the number of squares for 4 going to be? For 5? 25, because are they doing anything else other than just squaring it? So then my equation could be y equals, and since they want you to use n squared. All right, so then 6 squared would be 36, 7 squared would be, and 8 squared would be, and don't be afraid to use a calculator if you don't know those numbers, okay? Not a big deal. Questions on that? Right, I'm gonna scroll down to pattern B. Hopefully, or it's on the next page, so I can't scroll down. Hopefully someone in your group has it, or you can get it from Schoology. It's quadratic. All right, now pattern B. How many squares in step 0? 1. In step 1? Step 2? Step 3? Just based off of that, can you tell if it's linear, quadratic, or exponential? All right, and how do you know it's exponential? It's multiplying each time. What is it multiplying by?
2.
And it's consistent throughout. If you do that each time, it is multiplying by 2 each time, what it had previously. So then in step 4, what would I have?
16.
Step 5,
32.
step 6,
64.
step 7,
128.
okay, and step 8.
56.
All right, so we completed the table. If we had to make this an equation, what would the equation be? Anyone remember from last unit? Brian?
Y equals 3, then 1 plus 5 parentheses, 7, and 7.
Okay, so you're giving me, without the numbers in it, so that's a good start. Since this one, are they giving me a percentage for how much it's growing by?
No.
So then maybe I should use the B instead, because B stands for what? Okay, good. And what is the common ratio in this one? What are we multiplying by each time?
2.
So that could be 2 to the, and I'll put n because they want us to use n for step number. And also, what's my starting amount? Because that's what A is.
1.
Times 1. So really, we don't need to even put times 1 because it'll still be 2n, 2 to the n. But remember, for exponentials, it includes your starting amount also. That's just how we learned it from last unit. So questions on that? Okay, I think this is great to go over before the quiz. So your quiz is in Schoology. I'll give you the password right now.